Now, priority queues also has keys. They are priority queues are what we say are binary trees. And remember, but they are not binary search trees. So the name queue has come up because the position where we perform a delete operation, that's always at the root. Now let us look at this tree. As I told you, heaps are also binary trees. They are not binary search trees. So that is why you can observe here that 80 is the node, 70 is the right child. So in binary search tree, this property, I mean, the right child should be greater than the node. So this doesn't satisfy. So this is not a binary search tree, remember, but heaps are binary trees. And heaps are complete binary trees. So if you look at this, the property, there are two types of heaps, that is max heap and min heap. In max heap, the parent is always greater than its children. In min heap, the parent is smaller than its children. But when we talk about heaps, we consider that under hai. When we talk about heaps, we generally talk about max heaps or maximum heaps, where the parent is greater than its children. So if you look at this binary tree or this heap, I mean, it's okay. Let's for instance say that it's a binary tree. If you look at this binary tree, node 80 is there. Is its children smaller? Yes, 45 and 70. It doesn't matter where these children are. It can be 70, can be this side, 45 can be this side, doesn't matter. So here in this case, when we consider this node 80, both its children are smaller than 80. So at this stage, the property of binary tree is satisfied. Then at this node 45, both the children are lesser than its parent, that is node 45. So at this stage also it is satisfied. Now these nodes 40 and 35 are leaf nodes, so there's no doesn't matter. Whereas node 70, if you look at node 70, node 50 is smaller, so this node satisfies that property, but node 90 is greater. So what we do is, this is not a heap, this is just a binary tree. To make this as a heap, always have to remember that the node should be greater than its children. So in this case, it's node 70, which is the parent, and node 90 is greater than. So this violates this property at this place, 70 and 90. So what we do is, we call something as heapify. We will shift the node so that the heap property is satisfied. So 90 becomes its parent and 70 becomes its child. So at this stage it is satisfied, this property is satisfied. That is 90 is there, 50 is less than 90, 70 is less than 90. But at its parent stage, that is 80, 9, and its child is 90, it's not satisfied. So again we have to replace this with its parent, I mean swap parent and child. So when we swap parent and child, at every stage or every node, except the leaf nodes obviously, you can find that the property of a parent greater than the children is satisfied. So this is a heap. Now remember, this property what we are trying to check over here is known as relational property. So a heap in heaps, two properties has to be satisfied. One is the relational property, that is a node will be greater than its children if it's a max heap. A node will be smaller than its children if it is a min heap. But we only consider max heaps. So every node should be, its children should be smaller than that node. That is known as relational property. The other property is the structural property. So heap has to satisfy both relational and structural. In structural property, what we say is, we say that the heaps are complete binary trees. Complete binary trees, not full. They are complete binary trees. Now, this is an algorithm, simple algorithm for performing insert. Now, what happens is, let us first try to see what insert is, and then we perform adjust and how to perform delete operation. And let us first try to see how to insert. Now, consider insertion is nothing but we are trying to insert elements from a heap. Now here, the heap is empty, and 40 is the first element we are trying to insert. Now, when we are inserting 40, that will be the root of the binary tree, or the heap itself, root of the heap itself. Now, suppose I want to insert node 80. Look at this side, node 80. Now, as the next element. So, very first thing is, it has to satisfy structural property. So, node 80 is not inserted as the right child. It has to satisfy structural property, that is, a heap is a complete binary tree. So obviously, complete binary tree means we have to fill it up level by level and fill the nodes up level by level and within levels from left to right. So node 80 is inserted as the left child. But when node 80 is inserted as the left child of node 40, structural property is satisfied, but it is violating the relational property. So child and parent are swapped. So node 40 becomes child, node 80 becomes the parent. So when node 80 is inserted, it is inserted as the left child, and then to maintain the properties of the heap, the nodes are swapped, and now 80 becomes the parent of 40, or the 80 is the root of the heap. Now suppose if I have to insert node 35. If I have to insert node 35. Node 35 will not be inserted as the left child or right child of node 40 over here at this stage. Why? Because it has to maintain the structural property. So always it is inserted as the last element in each level. I mean, depending from left to right it is inserted. Actually, not last element, left to right it is inserted. So node 35 will be inserted as the right child of node 80. When it is inserted as the right child of node 80, it satisfies the structural property. Then we also have to look at whether it satisfies the relational property. That is, a node should be greater than its children. In this case, node 80 is there, and we have children 40 and 35, which are greater. Parent is greater than its children. So this is satisfied. So this is also a heap. Now we will insert another node as 90. So 90 node will be inserted as the left child of node 40, because this level all the nodes are full. So we have to binary, it should be a complete binary tree. So we start inserting as the left child of node 90. Left child of node 40. So now what happens is node 40 left child, structural property is satisfied, but relational property is not. That is, node 40 is smaller than node 90. So node 40 comes here at place of 90, and 90 comes in place of node 40. Then at this level, that is the second level, node 80 is there, which is smaller than node 90. It's not possible. So 90 gets swapped with 80. So ultimately we will have node 90, node 80, and node 40. So this is the 90, 80, and 40. So this part is the heap. The tree which you see on the right side is the tree after, is the heap after inserting node 90 and adjusting the elements. Then another node 45 I am inserting. So if I insert 45, I will not insert as a left child. I have to insert it as the right child of node 80. Now when 45 inserted, is it satisfying? Yes, it is satisfying both structure as well as the relational property, because node 40 and 45 are smaller than node 80. and 80 and 35 already satisfied. Then if I insert node 50 now, when I'm inserting node 50, it should be inserted as the left child of node 35. This is this satisfies the structural property because that is how we are inserting, and then but violates the relational property. So 35 is replaced with 50. So 50 comes here. So this part, the right side, what you see is a heap. 50 and 35 are replaced. Now, do we have to replace 50 with 90? No, because the property is satisfied here. So if you observe, wherever we are inserting from, that is at the leaf level we are inserting, at the last level we are inserting, from there we have to check its parent, then its parent, then its parent until we reach the root node to adjust the node so that the relational property is satisfied. So now let us look at the algorithm. Now here is the algorithm for insertion. We have an array A. In that array we will be inserting the nodes. So I is the position where it has to be inserted. Obviously it has to be, the item has to be, that is the last position has to be inserted. Then after insertion, after we add at the end position, we have to use and traverse till the root node. To do that, so that we have satisfied the structural property. To do that, we use a while loop I greater than 1. Because when I becomes less than 1, that means we reach the root. And A of I by 2 is less than the item. That is, the parent is less than the element which we are inserting. Then move to its parent. Its parent will be I by 2. That is why we have I by 2. And make I as I by 2. So A of I by 2, it's nothing but we are trying to go to the parent node, replace the parent node with I by 2. That is, the child is replaced with the parent. And then I is divided by I by 2 so that we go a level up. We move a level up. So if we look at the tree, the heap here, if this is I, if 90 is I, this will be I by 2. The second level node 80 will be I by 2. Its last level will be I by 4. So as we move up, so parent and child, if parent is I, child will be, sorry. If parent is, if the child is I, parent will be on the I by second index. If its parent will be at I by fourth index. So that is why we have to move each level by level. It's looking at its parent. And remember, when we are dividing I by 2, it's floor division. You will, suppose if there are 7 elements and 7th position, for example, let us go back. This is for 90 is node 1, 1, 2, 3, 4, 5, 6, 7. So node 70 as the 7th position. So when I divide 7 by 2, what will I get? 3.5. But we don't have floor division values for indices. So we may we don't have floating point for indices. So we use floor. That is, instead of 3.5, only 3 is considered. That is the nearest integer. 3 is considered. So if 70 is at index 7, 70 by 2 is 3, and which gives its parent. So if you can see, node 90 is 1, node 45 is 2, node 80 is 3. So 70 is a 7, 7 by 2 is 3, so it gives the parent. If 50 is their node, node 50 is at 6th position, 6 by 2 is 3. So again, it gives 80 as its parent. So here if you see, we have 50 and 70. 50 is at index 6, 70 is at index 7. So both when we divide, it gives 3 index 3, which is nothing but index of its parent, that is node 80. So that is what we are doing here and comparing with each and assigning. That is how insert is performed. Now adjust is nothing but the same problem, same thing over here. What we try to do, we look at delete, then we'll come back to adjust. And delete max, actually, delete max is nothing, as we have insertion. The same way we have deletion also. But remember, as in binary tree, binary search trees, you can delete any node, root node, any leaf node, any internal node you can delete. But in heap, deletion only happens at the root. On every time when you when a deletion is performed, it is the root node which gets deleted. So the algorithm for deletion is nothing but when the 0, that is there are no elements, then he is empty, you cannot delete. Otherwise, remove a of 1. Always, I'm telling you, when deletion happens, always the root node is removed, deleted. When root node is deleted, then the last node is replaced with the root node. So root node is deleted, the last node is replaced with the root node, and then adjust is caught. Let us first look at the practical, a way of deleting. We will look at an example of deleting. Now, let us look at this. Where is that? RNA. Let us look at this. Let us look at this heap. Is this a heap? Yes, 90 is there, 80, 35. Both are less, 40, 45, both are less than 80. Now, when we perform deletion, node 90 will be deleted. Node 90 will be deleted. Every time the root node is deleted. Node 90 will be deleted. Once node 90 is deleted, this node, this left subtree and this right subtree will be two different trees then. So what happens is, when node 90 is deleted, the last element from the heap, which is the last element? Node 90 is 1, 2, 3, 4, 5. Fifth element, which is 45. Last element is replaced with the root. So this node goes, this is replaced with the root. So 45 becomes the root node, and there is no what do we call, where is that marker? So 45 is replaced here, so this becomes 45. This instead of 90, this becomes 45. 45 is deleted. Then when this becomes 45, so always remember that the last element will get replaced with the root node. Then this satisfies the structural property because root node is there. You have its two children. It's the node 80's child. It's a complete binary tree. Structural property satisfied. But relational property will be violated. So what we do is, for relational property, we will check its children. Which children is greater? The left child or the right child? In this case, it is the left child. So left child is swapped, whichever is greater is swapped with its parent. So here instead of 45, we have 80. And here we will have 45. Instead of 80, we will have 45. Is it satisfying? Yes. Here we have 80. This is 45 and 35, which both are smaller than 80. Fine. This is 45. And here we have 40 as its child. So it's fine, satisfying the relational property. So ultimately, we get a tree which will have 80. And then 80 will have 45. 45. Its right child will be 35. And then 45 has its child 40. So this will be heap after performing the delete operation. And the element which is deleted is the 90. It's the root which is deleted. So every time in a heap when we delete it, the root which gets deleted. So remember that. Now let's come back to the algorithm of delete max. So last element is the first root node is deleted, which is at index 1. Last element is assigned at the root node. Then this satisfies the structural property. These two statements in line 8 and line 9 satisfy structural property. So now we have to satisfy the relational property. That is, we have moved 45 to 40 and the parent child. That is done using adjust. So adjust algorithm is there to, is there to, it is to adjust the elements such that the relational property is satisfied. If you look at adjust is just opposite. For example, when we had parent, you have child. So child divided by 2 gives you the parent. And parent multiplied by 2 gives you the child. But in child, we can have a right or the left child. So that is what we are doing. There we had seen an insert, I equal to I by 2. But here we are using a variable as j, and 2j we are using because always the parent and child will be at a different level. And when j is the parent, then child will be at 2i or 2i plus j. Anyway, so here we take the ith element, and if j is less than n, because now there in insert we checked I greater than 0 till I greater than, if I becomes less than I less than 1, if it's I greater than 1, if it becomes less than 1, what happens is you are crossing the root. So in insert you are moving from last level, last node till its root. In adjust, when we perform delete, you move from the root till the last element in the path, in the last element in that level. So item is taken, then j is less than n, you are saying, because nth gives you the last element. If j is less than n and a of j less than a of j plus 1, we are checking which two, who is greater, I mean the left child or the right child. So if left child is smaller, a of j is left child, j plus 1 is the right child. So if j is smaller than this, that means smaller than the right, that means we move j to the right side. So we do j equal to j plus 1. If we find at any point that it satisfies parent child, satisfies the relational property, that is parent is greater than child, we break. Doesn't do anything. Otherwise, we move to a down level. And down level is nothing but by 2. So j is the parent node, j by 2 will be the child node. And then this procedure repeats while loop till we go to the last element. So in insertion, we are inserting at we are inserting the node as the last element and moving till its root to satisfy relational property. In delete, since we are deleting the root node, last node is replaced with the root node, and then the last node is replaced with the root node, and then we traverse, or when we move from the root node till the last node in the level on that path to check whether parent is greater than, to check whether parent is smaller than the child. If so, then we replace it or we swap it. So this is how adjust works. Now there is something known as heap sort, and this heap sort works based on the heaps property. So if you look at the heap, now in this heap, this is a heap. Everyone knows this is a heap. Now when I perform delete operation, what happens? It's the root node which gets deleted. And root node in max heap always will be having highest element among, or that node will be the highest among all its children. So if you look at this, it's this node 90 which is the highest. Now when node 90 is removed, what will happen? Node 70 gets place of node 90, and then these two are property gets violated. So node 80 comes here, node 70 goes here. Next time when I delete, node 80 will be there, which is the next element, second element. So every time when delete is performed, it will be deleting the root node, and since the root node will be containing the highest element among the heap. So is every time when we perform delete operation is the highest element which gets removed. So we can use heaps for sorting purpose. Sorting is nothing but arranging elements in descending order. So when we sort, we perform, we can use heaps to perform sorting. So what we try to do is, when there are n elements in the array A, all the elements are traversed using a for loop and inserted. Now insert, we know, creates a heap. So a max heap is created. Then I equal to n to 1 step of -1. We start deleting. So this is a reverse for loop, decremented for loop. We start deleting. Delete max, will give you the maximum element, delete the root, gives the maximum. That maximum element, whatever is deleted, which is x, will be assigned to A of I. A of I starts from n, remember. So what we are doing, it's going reverse way from n. So first time when delete max is called, largest element is deleted when I is 1. When I is n. So A of n is the last element. So in that array itself, last element is the highest element which is stored. Next, again delete is performed, I becomes n minus 1. At second last position, second last element is stored. So delete max is called repeatedly for n number of times, so that every time a node which gets deleted will be the highest node among the elements remaining in the heap, and that is assigned to the array. So that is how we can make use of heap sort. Heaps, we can make use of heaps for sorting the set of elements. Then there is something known as an algorithm known as heapify. This heapify is nothing but again creating a heap itself, but insert was inserting each element by element and creating a heap. Heapify means we already have a tree, a binary tree. That binary tree, we convert that binary tree into a heap. That is known as heapify process. And obviously heapify also, you have to look at nodes and try to maintain whether it's a relational property or not. Obviously that tree has to be a complete binary tree, so that it's satisfies the structure property. But for relational property, what you have to do is you have to again call adjust. And adjust is called on every time on half, because when we select left and right nodes, they will be adjusted, simultaneously. If left is greater than right and you are making right, the left swap with its parent, then obviously half of the tree is done. So heapify, we will call adjust method again to balance the relational properties, so that the binary tree gets converted into heap. So heapify is nothing but converting a tree into a heap. So let us look at another example, the last example in this one. This is nothing but we have 100, 119, 118, 171, 121, 152, and 132. This is a complete binary tree, structural property satisfied, but relational property is not satisfied. That is why we will perform heapify. When we perform heapify, you can look at the stage 150, 118 is there, these two. So we are starting from the last n by 2. These two elements get swapped. That is 151, 118 get swapped. So at this place 118, 132, they both are smaller than 151. So at this stage it is completely the property is satisfied. Then here you can see at this stage for this part, 171, 112 is there, 119 is there. So 119 gets swapped with 171 because 170 is greater than 112. So at this stage also it is satisfied. Now we have to move to a level up, that is n by 2. So this is this level up. At this level we will be looking at its parent, 171, 151. 171 is greater than 151. So 100 is swapped with 171. But 100 comes here. But when 100 comes here, then 119 is over here, which is greater than 100. So again, this 100 comes here and 119 goes there. So this is how the binary tree is complete binary tree can be converted into a heap using heapify method.